So this is lesson 5.1 on areas under a curve. So this is the first lesson that I'm doing on this topic. So I'm going to kind of start from the beginning. When we first learn about area, it's probably in elementary school where we're taught certain formulas for really common shapes that we might encounter, such as rectangles or triangles. When we do area in calculus, the difference is that we're no longer dealing with some of those shapes that we're used to working with, like rectangles and triangles. Instead, we're looking at really complicated shapes, like the areas under certain graphs. This is calculus because the area or the height of these shapes that we're looking at is changing, right? And we know that calculus is the study of things that change. And so so we're interested in this question is like, can we find the area under this curve? So here we have an example on the far right-hand corner. So this will be, by the end of this unit, you'll be able to answer this question with an exact number. But today we're just going to talk about estimating this. So we have this function here, y equals x squared. And we're interested in finding the area under the curve. And when we say area under the curve, what we mean is that shaded region here that we have in that picture from the x-axis up to the curve, from x equals 0 to x equals 1. So again, by the end of this chapter, you're going to be able to answer that and give an exact value. Today, we're just looking at estimating that, right? And when we're talking about estimations, one of the most common ways we can just estimate it is by taking some of those formulas we learned back in elementary school and using some of those shapes that we're used to working with. So what we're going to do is split this area up into some rectangles, and we already know the area of a rectangle formula, so we can then calculate the area that way. So what we do is we decide to split it up into a certain number of regions. Now, how many regions you choose to split it up into is going to determine how accurate your estimate is. Okay, so if you're doing a practice question, typically they're going to tell you how many regions to use, but you want to use something convenient so the numbers are kind of nice. But here first we're going to start with 5 regions. So we're looking at this along the x-axis from 0 to 1. So if we do 5 regions here, each one is going to have a width of 0.2, right? And we see there the 5 regions. Now, when you split it up into 5 segments like this, you have a choice of how tall to make your rectangles. So this first example, both of the examples you see there are using 5 different segments with each with a width of 0.2. But on the left, for the one on the left, we're using the left endpoints of each of those segments to draw the height. So this is how you would go about doing this. In the first segment, the point on the left is at 0. So we would just have a rectangle with a height of 0 to start with. Then at the next one, we're going up to meet the function where it's at and drawing our rectangle over from there. And then for the next one, again, go up to the height of the function and draw your rectangle over from there. And then again, up to the height of the function, draw your rectangle over from there. And finally, for the last one. Okay, so notice how I've used 5 points on the curve for this estimate, and it's actually the 5 points that are on the left side. Okay, there's this point I didn't use right up here. Didn't use this. Okay, now for the example on the right, we're using, instead of using the left side of the segment to get your height for your rectangle, we're going to use the point on the right side. So over here for our first segment, I'm going to go to the right side and draw my rectangle that way. Okay, this is just as valid as an estimate, but we're going to get an overestimate for the height here in this case, or for the area. Okay, so notice how I'm using the points on the right side of each segment to get each rectangle, and we didn't actually use this point. Okay. So both of these are not very accurate, right? There is a lot of error. So I'm going to highlight the error in yellow, right? We have some error in between here that was missed in the left endpoint estimates. So, and then on the right, it's an overestimate. So we actually did too much. Okay. And what we're going to look at here below is what happens when we increase the number of rectangles. So as you can see in the pictures here, just visually, that yellow space that I've highlighted, the extra, actually gets smaller and smaller and smaller, and the estimates get better and better as we get more and more rectangles, right? It would be pretty tedious to calculate an n equals 30 estimate, right? That you see on the far right side. But what I want you to notice is that the estimates do improve as the number of rectangles increases, okay? So some observations here. So for this particular graph, because it's an increasing graph, you get a low estimate from the left. That's not always true, right? The left, and a high estimate from the right. And then the other observation to note is that the estimations get better as we increase the number of rectangles. So as we increase n is going to be the number of rectangles, estimates improve. Okay. These are called Riemann sums, by the way, because the mathematician named Riemann first used this type of estimating. Okay. So let's look now at a more general picture. Okay, so we're going to start with the left side. Okay, when you have this segment, or when you split up your region into the different numbers of segments, like we mentioned before, we actually have, so let's say there's n segments, we actually have n plus 1 points. Okay, so when you label the x values, a typical way to label them is just to start at 0 and go 0, x1, x2, x3, x4, all the way to xn. Okay, so when you're doing the left endpoints, what you end up doing is you end up using the left endpoints. Okay, so let me show you what I mean by that. Okay, so, and we call our left estimates L for left, and then N showing how many rectangles you have. Okay, so the area of a rectangle is length times width. Okay, and the width, the way we set these up, the width is always the same. And we call the width delta x, or change in x. You'll notice it labeled here as well. Okay, so the width is delta x. So for every single one of these rectangles, the width is always delta x. And then the height just depends on the height of the function at that point. So for this very first rectangle here that I'm highlighting in blue, the width would be delta x, and then the height would be whatever the function value is at x0, right? And then you would go and add the next one. So that would be the height at the second point, which is x1, and so on, all the way up till the very last rectangle here, which actually the height we would use is the function value at the second to last point there, because it's the one on the left side. It's not quite xn, it's xn minus 1. Okay, you could write this a little bit faster because every single one of these area calculations has the same width. We can factor that out if we want. Okay, and just put delta x on the outside, and then you would just add up all the heights. Okay, we could also use some summation notation here. So this big sigma says to sum everything up, we're going to go from 0 to n minus 1, and we're going to sum up delta x times f of xi. Okay, so this and this are the same things, just different ways of writing the same thing. Okay, but that's essentially what you do. Sorry, I missed a bracket here in that expression. Okay, so what we're doing is we are doing width times height, right, for every single one of those rectangles there. Okay, from the right endpoints, it's the exact same thing, except for the x values that we use are shifted over, right? So instead of starting with x0, we're going to start with x1. So notice my first rectangle here is created by the height from the point on the right side. That's why it's called the right estimate. So we call this estimate Rn. And the width is going to be the same. It's just delta x, right? And we would do f at x1 for our first rectangle. And we would go all the way until the last point here at xn. Okay, and we could use summation notation too, but this time we're starting at 1 and going to n. And actually, so you get actually two different numbers. You sort of sandwich your estimate in between those two. The other thing to notice is that these two are going to become pretty similar, almost the same, very, very close in value once your n gets very, very large, right? In fact, the actual area under the curve is equal to the limit as n goes to infinity of either ln or rn. So if you had if these rectangles were essentially infinitely thin, you would have the exact area under the curve and you would have no more error, right? That's what we're going to look at later in this unit, is how do you actually calculate that, assuming these intervals are infinitely thin. Okay, now let's do an actual example with some numbers here. So we're going to do 3 different estimates. I haven't actually talked about the third one yet, but we'll see that here. I think it's more obvious when you just draw it out. Okay, so we are given a function, f of x equals e to the x, okay? And our job is to find the area underneath the curve from 0 to 2. So I've drawn a picture of what that graph looks like here. I've used Desmos to create that. And part A says we are calculating R4. So that means we're coming from the right side, and we are going to split this into 4 intervals. So first thing I like to do is just label a few things on my graph. Okay, so I know this is the start, this is the end. Okay, and there's actually 5 different points I want to look at here. 1, 2, 3, 4, 5. Okay, so the first point, remember, is our x0. This is x1. This is x2, this is x3, this is x4, okay? So for my right side estimate, I'm going to look at each of these intervals and go to the right side of them to get the height that I want for my rectangle. So in this first one, I'm going to go to the right side and go all the way up until I hit the function, and that's where I'm going to draw my rectangle across from. So we'll see that's our rectangle that we're going to use right there. Okay, so the area of that rectangle would be 0.5 because that's the width, right? And then times the height, which is whatever the function value is at 0.5. Okay, I'm going to go slowly for the first one, and then I'll go a little bit faster for L4 and M4. The next one, I'm going to go to the right side of that interval, go up here. Oops, I just created a straight line by accident. Go up here and then over, okay, and there's my rectangle. Now the width here would still be 0.5, and the height would be the function value at 1, because notice that's where I took the height from. Okay, next one would be the height at 1.5. My width is the same for every single time, so I'm going to have a lot of 0.5s here. Times f at 1.5, and then finally the last one is 0.5 times f at 2. Okay, now I could have saved a little bit of time here because notice that the width is the same every single time, so I didn't need to write it every single time. I could have just written it once and then put the sum of the heights in a bracket. Okay, and what I mean by the function value at 5, we actually have the function here. It's e to the x. So I'm taking e to the power of whatever my x value is. Okay, so it's going to be e to the 0.5, e to the 1. These are the different heights. E to the 1.5 and e to the 2. Okay, so this is where I would need a calculator. I can't calculate those values in my head. So I'm going to put a little squiggly line because we're going to get, e is an irrational number. We're not going to get an exact value here. Type it all into a calculator and you'll get about 8.119. Now this is an overestimate for the area. It's a little bit too big because I've got all of these excess pieces that I'm highlighting in yellow, right, that make this an overestimate. Okay, you can either pause the video here and try L4 on your own, or you can do it along with me. But let's go to L4 now. Again, I've got my 4 regions, and I know it's 4 because the question just told me so, right? The question will usually tell you, or it should tell you, how many regions you need. But this time, and again, we've got 5 different points on the graph if you split it up into 4 regions. And this time we're going to go to the leftmost point to make our rectangle. So I'm going to draw the rectangles in first this time, actually. So we actually don't even use that point on the right at all. And this will be an underestimate. Okay. Again, each of the rectangles have a width of 0.5. So I'm going to save a little bit of time now because I know that. And the first one has a height at f at 0. Second one has a height, is the function value's height at 5. Third one is the function value at 1. And the fourth one is the function value at 1.5. So this would be e to the 0 plus e to the 0.5. And usually I try and keep my previous calculation in the calculator so that I can just go back and like use the arrow keys and just edit and just change the one number so that I save myself some time. So when you plug this in your calculator, you will get a long decimal that is irrational, but it's about 4.924. So you'll see this as a, those answers are pretty different. That's because there's quite a bit of error here. This one is an underestimate because of all those pieces I'm highlighting in yellow or missing from that answer. So the real answer is somewhere in between. Now we can actually do better. Now you can do better in 2 ways. One, you could just add more rectangles in and, but another way to get a better estimate is to kind of even out this error that we're getting, right? And so instead of taking the leftmost point or the rightmost point, we can actually take the point that's in the middle of each segment. So I'll show you what that looks like next. Okay, so same graph, same everything. This time we're going to do M4, and M stands for midpoint. So halfway through each little segment here. Okay, so here's the first segment between 0 and 0.5 that I'm going to make my rectangle from. I'm still going to have that same width, but this time the height that I'm going to use is going to come from the middle, from 0.25, halfway between 0 and 0.5. That's the point I'm going to use for the height of my rectangle. And then that way, what you'll see is you get a little bit of area that's too much on the left side, but then a little bit of an underestimate on the right side. So it kind of balances out a little bit more and it's a little bit more accurate. Okay, so that's our first rectangle. So again, all of the widths will be 0.5, so I'll just factor that out. So this time the height will be e at 0.25, right? Again, half the x value that's halfway between 0 and 0.5. And the benefit of this is you kind of balance out the error a little bit. Okay, so again, here I'm going to go halfway between 0.5 and 1 and use that as my height that I'm going to create my rectangle from. And again, I'm going to get a little bit of error on either side, but that's a good thing, right? That kind of balances out. It's not perfect, but it's better than before. So halfway between 0.5 and 1 is 0.75. I won't write those in every time, but I'll do it for the first 2. Okay, and again, the next one is going to be halfway here. I'm going to do, here's my point. So I get e to the 1.25. And finally, for the very last one, it'll look something like this. Okay, so this one should be the most accurate. E to the 1.75. And if you plug all that into a calculator, you get about 6.323. Most accurate. And that will always be the case. The midpoint should be the most accurate, just because, again, you're balancing out that error on either side. Okay. Yeah, so that's it for today's lesson. So the main idea is that, you should be able to do one of these Riemann sum estimates given a graph. You should be able to do it with or without the pictures. Yeah, that's it.